Okay. First things first, let's hand back some of your homework that's been graded. Cyrus, nope. Jonathan Mercer. And Jonathan Mercer. And Jonathan Mercer. There you go, and Cyrus. Okay. Well, that was quick and painless, huh? Pardon? 23rd, yeah, I think so. Wasn't that long ago, my clock I went by in my office, instead of 1 through 12, it had Monday through Sunday. And there was plenty of times I had to look at it to find out which one it was. Okay, you had a question about homework assignment number 13. Two locomotives approach each other on parallel tracks. Each has a speed of 155 kilometers per hour with respect to the ground. If they are initially 8.5 kilometers apart, how long will it be before they reach each other? So let's look at the, so here we got one train going this way. We have another train. Here we have a second train. Going the opposite direction. They're 8.5 kilometers apart. And they are both moving with respect to the ground at 155. Now, what is the question? What are they asking? They want to know how long it will take before they meet. Okay? Who could tell me what's the simplest approach for solving this, for coming up with this answer? Say again? Solve it for, oh, there's Cyrus. Did you sign in? Well, remember we talked about all motion is relative. All we want to know is how long will it take this train to meet up with this train? Well, instead of worrying about how fast this train is going relative to the ground, why don't we just determine how fast it's going relative to the other train? No, they're going the same speed, but they have opposite velocities. They're going in opposite directions. So what's the speed of this train relative to this train? Remember we talked, say again?
The second train.
Yeah, well, I'm saying depending on, by choosing our reference frame judiciously, it won't matter that this train is moving. Remember, how fast, if this train is going 155 kilometers per hour relative to the ground, how fast is it going relative to this train? (310 kilometers per hour relative to the other train. Now, you can just calculate, you can just work out its motion relative to that train. How fast will it cover that 8.5 kilometers? Yeah, distance equals rate times time. Yeah. You have 8.5 kilometers. If you divide that by 310 kilometers per hour, it'll give you a number of hours. That's the same thing as 8.5 kilometers times 1 hour per 310 kilometers. Kilometers cancel, and you have 8.5 divided by 310 hours, which you can then convert into minutes or seconds or whatever seems the most appropriate units. You did say that again?
I did 1/2 times 8.5 over 155.
Well, when you multiplied by 1/2, you were actually dividing by 2. Is that what you did? Okay, what you did was 1/2 and 8.5 kilometers divided by 155 kilometers per hour. What is that? That's 8.5 divided by 2 times 155. So, yeah. You may not have done it on purpose, but you did the same thing. You converted this train's speed to a velocity relative to the other train. Everyone see how that worked out? Any questions about any of the other problems? Number 11. See, what's the number 11? car traveling 95 kilometers per hour is 210 meters behind a truck traveling at 75 kilometers per hour. How long will it take the car to reach the truck? So look at a picture of what we've got. We have a car traveling at what speed? "95 kilometers per hour relative to the ground." Coming up behind a truck that's traveling at what speed? 75 kilometers per hour. Relative to the ground. And they are 210 meters apart. Okay? You could solve a complex system of equations where you look at the speed, at the how fast this truck is moving, compared to how fast this car is moving, and find the intersection point somewhere way down in the distance. Or, who has an idea about a simpler way to do it? Find the speed of the car relative to the truck instead of relative to the ground. Exactly. This car is going 95 kilometers per hour, but the truck's going 75 kilometers per hour. So how fast is the car going relative to the truck? The truck is moving away from the car, so the car is moving slower relative to the truck than it is relative to the ground. So as he points out, you then would take the difference in their speeds of 95 kilometers per hour minus 75 kilometers per hour. That would give you 20 kilometers per hour relative to the truck. Now, how long will it take the car to travel 210 meters at 20 kilometers? Is it 210 meters? Yeah, 210 meters at 20 kilometers per hour. See how that's done? Anybody want to take their homework back and change? All right, any more questions? All right, well then let's get started on the next chapter, or the next section. We're going to start this morning in section 2.4 with acceleration. And just a little heads up, y'all might want to, you're going to want to start taking notes, because we are going to be, I'm not going to start writing yet, we're going to be working out a set of 4 equations of motion. They're called the kinematic equations we're going to be working out today. And they are the 4 equations that you're going to want to know to work out the homework problems. Let's start by talking about acceleration. The average acceleration, I'm going to use the book's notation again, so that means average, not a vector. The average acceleration is equal to the change in velocity divided by the time it takes. That's the average acceleration. And if you'll recall, last week we talked about the average velocity, and then we talked about the instantaneous velocity at a single moment in time as being the limit at, where the velocity was change in position divided by change in time, and if you took the limit of the change in time as it got down to an infinitesimally small number, that would give you the instantaneous velocity at that point. Well, the same thing works with acceleration. If you look at the limit, as this delta t gets smaller and smaller, the limit as it goes towards zero is going to be the instantaneous acceleration at a given point in time. And if this were a calculus-based course, that's exactly how we would be developing these equations of motion. Instead, we're going to stick to a very limited case. Very limited case, but it's also a very utilitarian case. It's very common, actually, that you'll encounter this, and you're going to see why directly. We're going to restrict ourselves to constant acceleration. So we're only going to be looking at least for now, we're only going to be looking at acceleration that doesn't change. Who can think of a good example of an acceleration that's constant, that doesn't change? Anybody? About the acceleration of a body due to gravity. It doesn't change. As long as you're talking about the surface of the earth, the acceleration of a body falling in space is falling in the air on Earth is 9.8 meters per second squared, 32 feet per second squared, if you're using British units. So, I'm emphasizing this point right now that the equations we're about to work out only apply if you have constant acceleration. Okay? They don't apply if acceleration is changing. So that means that if you have a problem where something happens and undergoes this acceleration and then the acceleration changes to something different, then you have to solve that problem in pieces so that each problem has a constant acceleration. And then you can combine those pieces to get your final result. But you cannot use the equations that we're about to develop in cases where acceleration changes. They work out some examples here where they talk about an average acceleration. Car accelerates on a straight road from rest to 75 kilometers per hour in 5 seconds. What is the average acceleration? Car starts at rest, which means its initial velocity is 0. It accelerates until its final velocity is, what did we say, 75 kilometers per hour? Yeah. And it does so in what, 5 seconds? 5.0 seconds. So we would call this time 1 equals 0 seconds. And I wrote initial and final. I'll try to stay with the book and call it V2. And that means T2 would be 5.0 seconds later. The average acceleration then becomes 775 kilometers per hour minus 0 kilometers per hour divided by 5 seconds minus 0 seconds, or 75 divided by 5, which is 15 kilometers per hour. I'm sorry, 15 kilometers per hour per second. Now, this is not standard units. This is a perfectly mathematically correct answer. Acceleration is distance per unit time per unit time. In order to keep it neat, we would want to convert these hours into seconds. So we would do that by starting off with 75 kilometers per hour is how many kilometers per second. Then when we divide it by 5 seconds, we get an acceleration that would be in meters per second or meters per second squared. And I think they did that, and yeah, it worked out to 2 meters per second squared. Say again? Oh, by converting 15 kilometers per hour into kilometers per second. Go ahead and work. No, this is a good question. And we get one hour per 3,600 seconds, correct? So you divide that 15 kilometers by 3,600 seconds. "15 kilometers, remember, is 15,000 meters. And you divide that by 3,600 seconds. And did I do something wrong or did I miss something? I did do something wrong. I read the wrong answer when I wrote 2 meters per second. It's 4.2 meters per second squared. Yeah, when I read that 2 seconds, I was looking at the next example. Now, let me ask you a couple of questions. And I want you all to think about this and answer. If a car has 0 velocity, does that mean it automatically has 0 acceleration? Well, that would be getting into displacement versus distance, but think it through. if an object that has no motion is at rest relative to whatever frame of reference you're at, if it's at zero for its velocity, if that means it has zero acceleration, then how could it ever speed up? It couldn't. So in point of fact, just because something has zero velocity does not mean it has zero acceleration. But if it has constant velocity, does it have any acceleration? No, because that's the definition of acceleration, is change in velocity. If the velocity is not changing, then it is not being accelerated. And what did I just see? Oh, yes, I do want to point this out. I want y'all to remember that even though we're dealing with motion along a straight line or motion in one dimension, velocity and acceleration are still vectors. Okay? That means they don't just have a speed or a magnitude, they also have a direction. Now, since we're only working in one dimension, that direction can be handled with a plus or minus sign in front of the number. Okay, but it is important that you remember those positive and negative signs to keep your direction straight. That problem we looked at just a moment ago about the car overtaking the truck and how long it would take. If you got your signs wrong and you added those numbers instead of subtracting them, if you took the sum instead of the difference, then that would have completely changed the answer and it would have been wrong. Yeah, okay. Yeah, I remember they did this. We just did all this up here with the velocity 1 and velocity 2 and time 1 and time 2. They make some changes here in the way the notation is used. As a general rule, when we're working a problem, we're always going to assume that the initial time is 0 seconds. Okay? And so the total elapsed time will always be just t in the way they're going to start doing the notation here. And they're going to change over from, what they're basically going to do is they're going to switch over from V1 and V2. They're going to say your initial time is now t0. Your initial velocity will be v0. Your initial position will be x0. Okay? And your later time, velocity, or position will be t sub 1, v sub 1, and x sub 1. And actually, I'm pretty sure it'll all just be intuitively obvious when we start working out these equations. But just in case it brings up any confusion, don't hesitate to ask. Yeah. I told you we were going to work out a set of equations. Let's start with those now. Now, if you'll think back to last section, we talked about the average velocity was equal to the change in position divided by the change in time. Which we can write as x minus x naught divided by t minus t naught. Okay? The final position minus the initial position divided by the final time minus the initial time. Of course, since we are going to assume that t0 is, that the time always starts at t0, that becomes 0, and we can end up writing this x minus x naught over t, where t is just the elapsed time. Now, again, we're going to assume we have constant acceleration, so our actual acceleration will be our average acceleration. As long as it's constant, the average acceleration and the acceleration will be the same value. That's why it's important that we remember at all times these equations are for constant acceleration only. And we can write that acceleration as the velocity minus the initial velocity divided by time, by the elapsed time. Why are they doing this? Where are they going? I'm trying to follow this along in your book so it'll make sense when you refer to it. But before I do that, I need it to make sense to me. Oh, okay. That's what they're doing. They're saying that a common problem you're going to encounter is find out what is the velocity of an object after a given amount of time. Well, here we have acceleration is equal to the velocity, the change in velocity by the time. We multiply both sides by time. We end up with velocity minus acceleration times time equals velocity minus initial velocity. Add the initial velocity to both sides, and we get the initial velocity plus the acceleration times time will give you the final velocity. And this is the first of those four equations I told you we were going to start working on. Velocity is equal to initial velocity plus acceleration times time. Okay, now we're going to look at how you would go about calculating the position of an object. Its x coordinate, after a time t while it undergoes constant acceleration. Well, you'll remember we talked about the average velocity was equal to the notation, right? V naught. No, I don't. Scratch that. I'll get there. We'll get there in a minute, but yeah, that's what we're going to start with. We want to know, we know the average velocity is equal to the change in position divided by time. So that would be x minus x naught divided by time. Now again, we solve for x and we get v, the average velocity times time, equals x minus x naught. And we add x naught to both sides and we get x naught plus the average velocity times time is equal to x. But what happens when velocity is not constant? What happens when velocity changes, as in when it undergoes acceleration? Assuming the acceleration is constant, then we know that the average velocity will be equal to the initial velocity plus the final velocity divided by 2. That's just how you take an average. It's easy to visualize this in your head. If you think about it, a moving object starts off with some velocity. The velocity accelerates at a constant rate to some final velocity. The final velocity is going to be larger than the initial velocity. And as long as it changes at a constant rate, then the average velocity will be whatever the velocity was right at the middle between the two. Okay? Are there any questions about how we get this? Is it not clicking for anyone? Well, okay. Well, now, let's revisit our equation for x. Only now, let's replace the V average with this. Times t. Now here, okay, they do some. I made some fairly extensive notes here because they do. There's a point here where they say if you do the algebra, then you can solve this equation and come up with this result. But there's a lot there that is not intuitively obvious. That's why I'm working my way up to that point, and I want to go through those steps and show you how that derivation occurs, not just give you a formula and then expect you to just believe that it's true. Yeah. Okay. What we've got here, we've got V sub naught plus V over 2. Right here, we see that V is equal to V sub naught plus acceleration times time. So if we replace V here with that, we get x is equal to x sub naught plus V sub naught plus V is V sub naught plus AT all divided by 2 times t. Now here we can simplify this by noting that we've got 2v sub naught over 2 plus at over 2. These 2's cancel. So we can rewrite this equation as x is equal to x sub naught plus v sub naught with all of this multiplied by t plus v sub naught times t plus acceleration times t squared over 2. And that, again, is assuming we have constant acceleration. This is the second of those formulas that I was telling you about that you're going to want to remember. You're going to want to make sure you get it in your notes. Now, are there any questions about how we got this? We're saying that the position x is equal to the initial position plus the initial velocity times time plus 1/2 the acceleration times time squared. Okay, so technically speaking, these this should be written as position x as a function of t. Here we have velocity as a function of t, because its initial velocity is a fixed value, constant, it doesn't change, and the acceleration is a constant, because if it's not, these equations are not valid. Same here, initial position, initial velocity are just numbers, they don't change. What changes is its final position, which changes as a function of time. Did I miss one? 2, 6. I did. Yeah, I see it. And I did. I neglected to put down the one that, this one right here. The average velocity is equal to the initial velocity plus the final velocity divided by 2, as long as acceleration is constant. That's a third of the 4 equations. Now we're going to work on the final, the fourth and final of these 4 equations. This is one that you will need whenever you don't know what the total elapsed time is. When you're asked, how long does it take for this to happen, for this final position or this final velocity to be reached? Well, we can back up. Did I already erase it? No, it's still right there, isn't it? Yeah. It's still right here. So we're going to start back from here. I didn't skip a step, did I? X is x of naught plus that. No, that's what we had right there. We're picking up there. And we solve I've already erased it. But no, there it is. V equals V naught. We have this equation here. We'll solve this equation for t. So we start with V equals V naught plus AT. That gives us V minus V naught equals AT. And V minus V naught divided by A equals T. Now, that we can substitute into this equation and write x is equal to x sub naught plus v naught plus v over 2 times t, which is equal to this, v minus v naught divided by a. This is the one I was telling you about in the book. All they say is we solve this for v squared and obtain, but they don't show you, they don't go through any of the steps of how to derive it. And I want you to see how this is done. So that's a good question. Yeah, I think we can get there. That'll be, will that leave for Thursday? I mean for Friday? 2.6, 2.7, and yeah, 2.8. Yeah, we'll be good. But I do want you to have these 4 equations because you're going to need them tomorrow in lab. Because we're going to kind of jump ahead a little bit when we do the free-falling body in lab tomorrow. So, let's start by, we want to simplify. In order to simplify this, we're going to multiply this term by a over a, and this term by 2 over 2. Because you can multiply anything by 1 and you don't change it, correct? So we've got x equals x naught plus a over a times v naught plus v divided by 2 times 2 over 2 times v minus v naught over a. And that simplifies to a times v naught plus a times v, multiplying through, divided by a2 times 2v minus 2v naught over a2 and when we multiply these two together, we get, and I'm going to give myself a little more room to work here. First gives us 2a v naught v inner plus 2a v squared outer minus 2a v naught squared last minus 2a v naught. All divided by 4a squared. a2 times a2 is 4a squared. Well, we got this cancels here, and we're left with x naught plus 2av squared minus 2a v naught squared divided by 4a squared. We can factor out a 2a, and that gives us x naught plus 2a times v squared minus v naught squared over 4a squared. This 2a cancels one of these, and we're left with x sub naught plus v squared minus v naught squared over 2a. That is x. Now, is that the final form? Not quite. Oh yeah, then this we solve for v squared and if we solve that for v squared, we get x minus x naught equals v squared minus v naught squared over 2a. 2a times x minus x naught equals v squared minus v naught squared. So v naught squared plus 2a x minus x naught is equal to v squared. And that is the formula, the equation that we've been working towards. And that is the fourth of the equations that you want to know. V squared is equal to v naught squared plus 2a x minus x naught. And those are the four, what the book calls your four kinematic equations. Something for y'all to think about between now and tomorrow when you come in for our lab on free fall. What if we changed x to y? We're still moving in one direction. And we changed a to g, or minus 9.8 meters per second squared. Then you would have the equation for a free-falling body in a uniform gravity field on Earth of y equals y sub naught plus v sub naught t minus 1/2 g t squared. And that's probably the equation your friend was working through that you were talking about at the beginning of class. Have I handed back everybody's homework? You got labs here. Homework? Yeah. Thank you. Thank you. Okay.
Got my name.
I'm sorry, say again?
So tired.
Preaching to the choir, sister. You're preaching to the choir.